All right, calculus, let's do a super free response question on differential equations and slope fields. So this says the solutions to the differential equation given here also satisfy this second derivative. Let y equals f of x be a particular solution to that differential equation, and with the point 1, 2. And then the first thing we're supposed to do is draw the slope field. So we have dy dx is xy cubed, and so we can make a little table of x values and y values, and then what slope that will be. So if we take the point 0, 0, then the derivative there will be 0. And so we draw a little slope of 0 at 0, 0. And let's pick another point like 2, 1. X is 2, y is 1. We have 2 times 1 cubed, which is 2. And so at 2, 1, we're going to draw a little slope of 2. So I'm going to go ahead and have you pause and fill the rest of these out, and then unpause and see how you did. Okay, so there you have all of your little tick marks for the individual slopes. And then the rest of part A says to draw a solution curve through the point 0, 1. So that's this point right here. And so this looks like it would go something like parabola-ish looking, at least in that spot right there. So that's the solution through that point. All right, part B, describe all points where the particular solution to the differential equation has horizontal tangents. Horizontal tangents occur where the slope is equal to 0. And so we want to find where dy dx is equal to 0. And since dy dx is equal to xy cubed, that is equal to 0 anywhere that x equals 0 or y equals 0. Those are all the places that horizontal tangents will occur. Part C, verify that that is the second derivative. So in order to do that, we need to take the derivative of the derivative to get the second derivative. So we're going to take xy cubed and take the derivative of that and verify that it is what we were given. So it's just kind of like a little proof. So xy cubed is dy dx. And so we need to do product rule to take the derivative of that. So the derivative of the first is 1 times the second plus the first, which is x, times the derivative of the second, which is 3y squared dy dx. And so then we're going to plug into dy dx, we're going to plug in xy cubed so that our second derivative is all in terms of x and y. So d squared y over dx squared is y cubed plus 3xy squared times dy dx, which is xy cubed. And then we're just trying to make that match the second derivative we were given. And so I'm going to rewrite this as y cubed plus 3x squared y to the 5th. And then we're going to take out a y cubed, leaving us with 1 plus 3x squared y squared. That is the second derivative that we were given, and they match. And so we have shown that that is correct. And then we want to know, does f of x have a point of inflection at the point 1, 2? A point of inflection occurs when the second derivative is equal to 0. So we want to know if we plug into the second derivative, is it going to equal 0? And then we have to figure out if it does, if it's going to also change signs. So d squared y dx squared to be evaluated at the point 1, 2 is going to be 1 cubed, nope, 2 cubed times 1 plus 3 times 1 squared times 2 squared, which is not looking to be 0. And therefore, there is not a point of inflection at the point 1, 2. And so we need to write that out into a sentence, except I ran out of room, so I'm going to squeeze it in. So we're going to say there is not a point of inflection, or a POI. There is not a point of inflection at 1, 2, because the second derivative does not equal 0 there. So d squared y dx squared is not equal to 0 at 1, 2. Part D, does y equals f of x have a relative minimum, relative maximum, or neither at the point 1, 2? Relative max and mins occur when the derivative is equal to 0. And so we're going to plug into the derivative and see if that equals 0. So dy dx at the point 1, 2 is 1 times 2 cubed, which is 8. So again, no, f of x does not have a relative max or min. F of x does not have a relative max or min at 1, 2, because the derivative dy dx is not equal to 0 at that point 1, 2. Part E, write the equation of the tangent line at x equals 1, and then use this tangent to approximate the value of 1.5. So how do we write the equation of a tangent line? We need a slope, which is dy dx, and a point. That's how we write the equation of a line. So the point is 1 something. The slope is at x equals 1. So we must have a y value for 1 somewhere. And that's what we were given at the beginning, the point 1, 2. So we know that our point is 1, 2. And so we need the slope at 1, 2. So dy dx at 1, 2, we found in the last problem to be 8. And our point is 1, 2, so y minus 2 equals 8 times x minus 1. And you can leave that like that. And then we need to approximate when x is 1.5. So y minus 2 equals 8 times 1.5 minus 1, which will be y minus 2 equals 8 times 0.5, which is y equals 6. Okay, part F says, is that we just found an underestimate or an overestimate of the actual value of 1.5. So if we think about the concavity, so at 1, 2, we're going to use part C. We saw that the second derivative is positive, and so I would just say that this is going to be concave up at 1, 2. I don't know where on that curve 1, 2 is, but if I take anywhere and I put the point 1, 2, and I draw a tangent line and say this is then 1.5, then my line underestimated the actual point on the curve. And so here we can say that part D is an underestimate of the actual value of f of 1.5 because the second derivative, d squared y over dx squared, is positive at 1, 2, and all of the first quadrant is really what we should say. So it's always positive over there. Is positive. Let's change that in the first quadrant. And therefore f is concave up. Okay, now we're going to find the solution to the differential equation with the initial condition. Find the solution of the differential equation. This is where you do your separation of variables. So we're going to rewrite it. dy dx is xy cubed. And then we're going to separate the variables. Y is on the left, so 1 over y cubed dy equals x dx. And then we're going to integrate both sides. And I'm going to write this as y to the negative 3 dy equals the integral of x dx. And then integrate both sides. This will be y to the negative 2 divided by negative 2, so negative 1/2 out front, equals 1/2 x squared plus c. And then we need to find c, so we're going to plug in the point 1, 2. So when x is 1, y is 2, so this is negative 1/2. 2 to the negative 2 will be 1/4. Those 1/2 times 1 plus c. That's negative 1/8 minus 1/2 equals c. So negative 1/8 minus 4/8, that's negative 5/8 for c. So now we're going to plug that in to when we found it, which is right here. So negative 1/2. I'm going to write this as times 1 over y squared equals 1/2 x squared minus 5/8. And then we need to solve for y. So I'm going to multiply everything by negative 2. So 1 over y squared equals negative x squared minus, plus, because we're going to multiply by negative 2, 5/4. And then we need the y squared on top, so you can actually just flip both sides or multiply this side by y squared and divide the other side by the x and the 5/4. So we get y squared equals 1 over negative x squared plus 5/4, which you can leave like that. You do not have to simplify. And so y equals plus or minus this thing. And then we actually need to decide if it's plus or minus, and we're going to decide based on the point 1, 2. And since we need the y equals 2 to be positive, we are going to take the positive and not the negative. So I'm just going to erase the negative there. Actually, you can erase the whole thing. It is the positive value. And there you have it. Okay, so the last piece of this is that use your solution to find f of 0. So f of 0 means we're just plugging in 0 for x. So that's the square root of 1 over 0 plus 5/4, so 1 over 5/4. And we're going to leave that just like that. And that is our super free response question for differential equations in slope fields. Enjoy.